Hi, it's Luke. We're going to go through some examples of some quantum chemistry calculations, and yeah, we're just going to get straight into it. I think we've got about 3 or 4 to do in this video. We'll see if we can do that or not, I don't know. So, first example is, show that the following wave function is equal to the exponential of minus alpha x, and we need to show that that is an eigenfunction of the operator of the second derivative with respect to x, essentially. So we'll set up the equation. We've got the operator, essentially one of the eigen equations, and if we plug in the numbers, plug in that the wave function is equal to that. We know the wave function, we know the operator, so we can plug that straight in. If we differentiate it once, we get this, the minus alpha comes to the front. And if we differentiate it again for the second derivative, we get alpha squared this time. And we take in a minus alpha times minus alpha to get a positive alpha. And that's e to the x. And therefore we can say that the derivative of that is equal to alpha squared multiplied by the wave function, which is equal to minus e to the minus alpha x. So therefore we can say that the operator times the wave function is equal to alpha squared e to the minus alpha x, and that is equal to alpha squared times the wave function. We can say that alpha is independent of x, so the wave function is an eigenfunction of the operator. And this is an exam statement when a question is complete, so it's good to put that right at the end anyway. A second example, we're going to be looking at another particle in a box of length L. So if we're given the two lowest energy wave functions, which is the first and second wave function, are this and this, not much difference. In fact, completely the same, apart from there's a 2 in front of the pi there. We need to show that they're orthogonal, and to show that they're orthogonal we need to do the wave function 1 multiplied by wave function 2, and that needs to equal 0 when they're orthogonal. So first off, we'll sub in these numbers. We could take a factor of 2 over L out straight away, which is nice. It's very nice. And the half also goes away too, because we're multiplying them together, I believe. I think that's the reason it goes. Anyway, we'll continue. Maybe it comes back. I can't remember. So yeah, that gives us that. We know the relationship between sine 2x. We know sine 2x equals 2 cos x sine x. So if we sub in this knowledge, because essentially we've got sine 2x here, so if we sub in that knowledge, we'll be replacing sine 2x with 2 sine x multiplied by cos x. So once we've done that, we'll get 4 over r. The 2 is taken out of the integral, and then we've got sine squared x because we've got 2 of them now. So multiply those together, you get sine 2x, and then we've got the cos term as well, excuse me. If we integrate this, integrate in sine, well, there's one way of looking at it. If you differentiate sine cubed, pi x over L, this gives an additional factor of pi over L, so we have to multiply originally to remove the constant, which that is essentially one way of looking at integrating the above term. So if you integrate sine And if you differentiate sine cubed pi x over L multiplied by L over 3 pi, you'll get the product at the top. Anyway, since sine pi cubed equals 0 when x equals L, and when x equals 0, sine 0 will equal 0, we can say that 4 over L is equal to 0 minus 0, and that's it, it equals 0 essentially, which shows that they're orthogonal, which is what we were looking for at the start. An additional way of integrating this term, which is easier in my opinion, is by using the substitution method. So if we say that y is equal to sine pi x over L, and we can say that dy, which is the differential of sine pi x over L, is equal to cos pi x over L times pi over L dx. And if we can sub that in, we'll get y squared dy, and we know that dy is equal to what we had. But if we integrate the y squared in terms of dy, we'll get y cubed over 3, and we've got 4 pi outside the bracket, which the 4 pi is from the L cancels with the L that was usually there, which means you'll get a pi instead, because you take out pi over L, and that will, this pi over L, sorry, you take out that pi over L, and that gives you 4 over L times pi over L, and once you times those together you'll get 4 over pi. Anyway, back down here, if we sub that back in, obviously saying that y equals sine pi x over L, we can show that 4 over 3 pi times by sine cubed pi x over L, which is essentially the same as this equation here, which has got the star. We've just cancelled the L's, and this is obviously between L and 0, and once you've substituted all the numbers in, blah blah blah, you'll get 0 as well, which shows they're orthogonal. Another question here is looking at the probability that the particle will be formed within L over 4 of the centre of the box. So what it's asking us is, what's the probability that the particle is going to be in between L and L over 4 and 3L over 4? We want to know the probability of that. One thing we do know is that the wave function is symmetric around the centre of the box, as you can see just there, very poorly drawn, but that's supposed to be symmetrical. So we can say that the total probability is 1, or the probability that it will be between that is 1, which is the total probability that we'll see it in the box. The total probability we'll see it in this whole box is 1, minus this part, essentially, and then minus this part. So between 3 over L, or 3/4 L and L, and between 0 and L over 4, which is represented by that and that. And because of this known symmetry that we know, because it's symmetrical around the centre of the box, we can say that probability is 2 times the value of either L over 4 to 0, or we could have used the other one too. But I think L over 4 to 0 is actually easier to look at. So we're going to be integrating overall space between L over 4 and 0 by the wave function squared, and that's equal to 2 over L, L over 4, sine squared n pi x over L, and that's one of the terms that we've been given earlier, which was in the last part of the question, because this is part of the same question, I believe. So we're given these values here, and that clicks in to this part here. So we know that 2 sine squared x equals 1 minus cos 2x, which we saw earlier. If we sub that in, we'll get 1 over L, because we're going to have to divide by 2 outside the integral, and then we'll get 1 minus cos 2n pi x over L dx. We're going to want to integrate that term, which we've done something similar before. Integrating 1 gets us x. Integrating minus cos gives us minus sine 2n pi x over L plus the terms that we have there, and that's the integral done. And then obviously we're integrating between L over 4 and 0. So when x equals L over 4, we're going to sub all this in, and you get the above. And when x equals 0, we have the above equaling 0. So now we're going to have to look at when n equals 1. And if we sub all that in, we get around 0.09. And when n equals 2, because these are the wave function numbers, we got wave function 1 and wave function 2 before, if you'll remember. When n equals 2, we'll get 1/4. So the probability equals 1 minus 2 times what we calculated. So when n equals 1, the probability that we'll find it in the middle of the box is 1 minus 0.09 times 2, which is 0.82. And when n equals 2, it'll be 1 minus 0.25 times 2, which is 0.5. The probability of n equals 1 is higher because the wave function is that as shown, so there's more obviously in the box. And then when n equals 2, there's wave function outside the box. The probability is the wave function squared, so if it was a probability, this would be all in the box with just a node in the middle. But n2 does have a node right in the middle, and also it doesn't, you can't see it in the other part. But the probability is a wave function squared, so it will have a node in the middle, which is in between L over 4 and 3L over 4, which means there is less chance of seeing it, only 0.5 instead of 0.82. The final example for this one is showing that x bar and px bar are complementary. So, as we mentioned in the first video, I believe, to be complementary, these two wave functions need to be not equal to 0. If they were incomplementary, they'd have to equal 0. So x, we can call x because that's a position moderator, and px is the momentum moderator, which is given as that. If we put that in a square bracket, multiply out the bracket, we'll get x bar px bar, and the wave function minus that. If we sub in what we know for each one, we'll get that, as you can see. And then what we'll need to do is to tidy it up a little bit. Once that's tidied up, so we've multiplied that out the bracket to get that. We've just left that as it is. Well, we've done minus minus, which is to a plus, and then we've got this x and the wave function term, and we need to use the product rule for that. So first off, we're going to differentiate x first, which equals 1, and we're going to multiply by the wave function for the first term, and then the second term we're going to differentiate by the wave function and then multiply by x. So once we do that, we get this term here, which is this, because this term we want to differentiate, but we've got two terms here. It's not just in terms of x, it's not just in terms of the wave function. So we can differentiate this straight up. Oh, we've not differentiated yet, sorry, my bad. So if we differentiate in terms of x, we get 1, which just leaves us with this. And then if we differentiate in terms of y, we get this. These terms will cancel, not y, sorry, the wave function. And that just leaves us with I, the h bar, the wave function, is not equal to 0, because the wave function can't equal 0. Otherwise, as we know, it won't exist. So, for example, another just fact here is if we took the y component of momentum to equal 0, because y is not dependent of x, so you're not doing the product rule in the differentiation, because it won't be the product rule here. You'll just be able to do it by y, or the y will just be left independently. You won't form this term. So this shows that we can know the position of the x and momentum of y at the same time, but not the position of x and momentum of x at the same time, position of y, momentum of y at the same time, etc., etc. And that'll end the examples. Hopefully this has cleared things up a little bit from the first video I did on quantum chemistry. The examples definitely helped me. I'm going to personally do some exam papers later. But next time we're looking at time-independent perturbation theory.